We've got some fresh images of Threeey Atlas, a third ever interstellar object observed from Earth, currently racing through our solar system. Now, astronomers have captured that moment live.
The universe just pulled off something extraordinary. Within weeks, NASA caught two violent star explosions lighting up the galaxy.
Now, until recently, we haven't seen dust being pushed back behind the object by the solar radiation pressure.
Then, out of nowhere, an interstellar visitor named Threeey Atlas swept past Mars. The odds of such perfect cosmic timing are almost impossible, yet it happened right before our eyes. What if these aren't random events, but signs of a universe more alive and connected than we ever imagined? A cosmic coincidence. On July 1, 2025, the Atlas Survey telescope in Chile picked up a dim, fast-moving point that didn't match any known orbit. When astronomers ran the math, the numbers didn't close. The path wasn't a loop around the sun. It was open, like a slingshot line cutting straight through the solar system and back out again.
It is only the third time we have detected an object that has come from beyond our solar system.
That shape had only one meaning. It came from beyond. The object was soon named Threeey Atlas. Threeey for the third interstellar object ever recorded, after the famous Oumuamua and Borisov.
This object has just been discovered. Threeey Atlas was discovered on July 1st by the NASA-funded Atlas Survey.
For astronomers, that was huge. You can study comets all your life, but nearly every one of them was born right here under our own sun. Interstellar ones are travelers from completely different systems, messengers carrying clues about worlds we'll never see. Weeks later, while telescopes continued to track the newcomer, the night sky itself seemed to erupt. Two distant stars in opposite corners of the Milky Way flared almost at once. In one, buried deep in the constellation of Sagittarius, a distant point of light suddenly blazed like a spark from nowhere. In another, across the sky in Centaurus, something just as violent went off. The first warning came from NASA's Fermi Space Telescope, the kind of satellite built to watch for the universe's biggest explosions. It had picked up a rush of gamma rays, light so powerful that only the most extreme events in space can make it. The source was logged as V7994 Sagittarii, a nova, a star that had just blown up in spectacular fashion. Barely a breath later, another alert flashed from a different direction. NASA's Swift satellite, an orbiting eye tuned to X-rays, caught a fresh burst of hard radiation from a star now listed as V1935 Centauri.
The satellite detects the gamma ray burst and it sends a message down to the ground.
For astronomers, that kind of double strike, one nova glowing in gamma rays, another in X-rays, is the universe's version of a siren. Those alerts weren't rumors or guesses. They were precise, time-stamped signals. Fermi's instruments saw the Sagittarius eruption in the third week of September, and Swift's cameras locked onto the Centaurus blast almost immediately afterward. The brightness of both stars began climbing fast, and observatories around the world started tracking their rise. For anyone who follows these outbursts, it was already an exciting week, but the universe wasn't finished showing off. In the first week of October, right as those two distant novae were still glowing in the background, Threeey Atlas made its closest pass to Mars. The timing was exact. Around 4 a.m. UTC on October 3rd, the object swept about 18 million miles from the red planet, close enough, on cosmic scales, to call it a neighbor. Think about that. A comet from another star system flying past one of our own planets, while two stellar explosions light up the galaxy in the same span of weeks. Nobody believed the novae had anything to do with the comet. They were far too distant, but the coincidence was too wild to ignore. The sky felt alive, as if the universe had decided to put on a show. Each telescope alert meant the same thing. Something had just dumped an enormous amount of energy into space. Gamma rays from Sagittarius, X-rays from Centaurus, and a comet that wasn't supposed to exist here, passing a planet right in our cosmic backyard. The details of Threeey Atlas only made it more fascinating. Unlike the mysterious Oumuamua, which looked like a tumbling cigar of rock, or Borisov, which behaved more like a normal comet, this one had its own personality. Big telescopes showed a glowing head with a faint tail, suggesting dust and gas were streaming off it as sunlight hit its surface. It was racing through space at over 100,000 miles an hour, and its path around the sun was a perfect open curve, proof it would never return. In other words, this was our single chance to study it. After this brief swing through the inner solar system, it would disappear into the dark forever.
2023 DZ2 was a significant asteroid. A rock that size might only happen a handful of times per century.
The timing with Mars mattered for more than drama. With Mars nearby and orbiters around it, astronomers gained a second line of sight, different lighting angles, and a steady reference point to measure against. It was like having a moving camera crew right next to the action. But before anyone could link those sudden flares to our new visitor, scientists had to ask, what exactly makes a star explode like that? The truth about stellar explosions. Every nova starts the same way, with a pair of stars locked so close together that they share more than light. One of them is dead, a white dwarf, the compact Earth-sized core left behind after a star like our sun burns through all its fuel. The other is still alive, a normal star quietly shedding gas. And because they orbit each other so tightly, the white dwarf's gravity begins to pull that gas away, stealing it bit by bit. Over time, hydrogen from the living star rains down onto the dwarf's surface. It doesn't mix in, it just piles up, forming a thin layer of stolen fuel. Imagine laying down sheet after sheet of tinder on a mountain of stone. When enough builds up, the base of that layer gets so hot and so compressed that the hydrogen fuses all at once. The result is an enormous surface flash, a burst of nuclear fire that sweeps across the white dwarf like a global detonation. To us, watching from thousands of light years away, that sudden explosion makes the system flare like a new star in the sky. That's actually where the word nova came from, Latin for new. Ancient astronomers thought a brand new star had appeared out of nowhere. In reality, it was an old one coughing out stolen fuel in a single furious breath. But make no mistake, this isn't a supernova. A supernova is a final death scream that rips a star apart or annihilates the white dwarf completely. A nova, by comparison, is a violent outburst, but the star survives. Think of it less as an ending and more as a cycle. The white dwarf borrows fuel, builds pressure, flashes in a nuclear eruption, calms down, and starts the whole process again. Some of these star pairs repeat the act every few decades. We call them recurrent novae. Others stay quiet for centuries before flaring up again. Either way, the ingredients are the same. A dense white dwarf, a nearby companion star, and a runaway burst of fusion that releases more energy in a few hours than our sun gives off in weeks. When that happens, the system brightens almost instantly. The blast throws off a shell of gas at thousands of miles per second.
Dust being pushed back behind the object by the solar radiation pressure.
So fast it could cross the United States in less than a second. As that hot shell expands, it crashes into older, slower material still floating nearby, and that collision creates enormous shock fronts. The space version of sonic booms. Those shocks are what make novae so interesting. They don't just glow invisible light, they pump out the hardest, most energetic light there is. When the shocks form, particles inside them get whipped to near-light speeds, heating to millions of degrees. That's when we start to see hard X-rays and even gamma rays coming from the blast. If you think of light as a ladder of energy, visible light sits somewhere in the middle. X-rays are near the top, the kind that can pass through your bones. Gamma rays are the very top rung, photons carrying so much punch that only violent cosmic events can make them. Those signals are exactly what appeared in September 2025, when two novae flared in different corners of the Milky Way, and both screamed across the spectrum in high energy. In Centaurus, V1935 Centauri kept proving just how fast and violent it was. Swift's instruments caught the hard X-rays almost the moment the blast began, and Fermi's gamma-ray telescope confirmed the shocks were already accelerating particles to extreme speeds. Most novae take days to reach that stage, but this one ignited almost instantly, showing that the explosion had slammed into thick, nearby gas right from the start. It climbed to roughly 6th magnitude, barely visible to the naked eye under dark southern skies. So for a short time, anyone standing outside in the right hemisphere could glimpse the breath of a system nearly 10,000 light-years away. Over in Sagittarius, V7994 Sagittari showed the same high-energy signature. Fermi registered the gamma rays, and within days, observers worldwide were already logging brightness data and spectra to trace the chemistry and motion of the ejecta. But it looked strikingly red in telescopes, not from the eruption itself, but because heavy dust along the line of sight to the galactic center absorbed most of the blue light. Even so, the gamma rays cut through the murk without trouble, showing that the blast was every bit as fierce as the one in Centaurus. Swift's X-ray telescope picked up the searing plasma where the shocks collided, temperatures so high they could melt metal in an instant.
An X-ray telescope and an optical ultraviolet telescope at the possible location of the gamma-ray burst.
Fermi's LAT instrument caught the gamma rays born when those ultra-fast particles plowed into gas and photons, turning their motion into even higher energy light. On the ground, spectrographs split the nova light into colors, tracking how hydrogen, helium, and heavier elements shifted red or blue as the gas raced toward and away from us. The Very Large Telescope Interferometer in Chile went even deeper, linking its massive mirrors to watch the shell expand in real time. It could actually trace how the ejected gas grew, twisted, and reshaped, whether it spread out smoothly or erupted in uneven knots and jets. Each nova turned into a miniature laboratory for shock physics, letting scientists see energy move through matter under the most extreme conditions. Every bit of data, X-rays, gamma rays, visible light, became another piece in the bigger puzzle of how the galaxy radiates at its highest energies. And through it all, one fact stays constant. Those gamma rays and X-rays might be unimaginably energetic, but they do not reach across the galaxy to affect anything here. The light travels for thousands of years before it arrives. It carries information, not force. Now that you know what was lighting up the sky, let's meet the traveler that passed right through it. Inside the strange life of Threeey Atlas. Threeey Atlas only got more interesting after its first sighting. A few weeks later, the Hubble Space Telescope captured razor-sharp images that showed a small, icy nucleus wrapped in a faint halo of dust. Estimates soon narrowed down its size. The core looked to be somewhere between about 1/4 of a mile and a few miles wide, with Hubble's favored number sitting near 3.5 miles across.
We'll pick out objects that are moving inside of the four frames, and we have to identify if they are real or if they are false detections.
And it's moving fast. Roughly 137,000 miles per hour. That's so quick that the sun's gravity will never hold on to it. 3. Atlas will dive in, loop around once, and shoot back into the dark forever. From the moment it was confirmed, telescopes around the world locked in. In late July and August, NASA's Swift telescope aimed its ultraviolet sensors at the comet and found the ghostly glow of OH, short for hydroxyl, a chemical that appears when sunlight breaks apart water molecules. That single clue let scientists figure out how much water the comet was venting every second, and the number was staggering. They estimated roughly 1.36 times 10 to the power of 27 molecules per second, which equals about 40 kilograms or 88 pounds of water every second. For a comet still more than 270 million miles from the sun, that kind of activity is wild. Most comets stay quiet that far out. The only way it makes sense is if a good chunk of its surface was already active, constantly venting gas and icy grains. Some of that water, it turns out, probably came from those tiny ice grains that lifted off the surface and then evaporated as they drifted outward, creating a kind of shimmering snowstorm around the nucleus. In short, Threeey Atlas was snowing off itself. While Swift was counting molecules, big observatories on the ground were breaking down its light into a spectrum, the rainbow signature that tells you what atoms and molecules are there. The first chemical fingerprints to appear were familiar: cyanide, often the earliest and easiest gas to detect in comets, and then hydrogen cyanide, a cousin that helps scientists trace where those ices might have formed long ago. But soon, something surprising showed up. Lots of neutral nickel, and for a while, almost no iron. Later, data from the Very Large Telescope finally spotted iron lines, but the balance between nickel and iron still looked strange. The ratio of nickel to iron was far higher than the sun's usual mix, and higher than what we've seen in most comets from our own solar system. One possible explanation is that these metals aren't escaping as pure atoms. They might be hitching a ride inside fragile compounds called metal carbonyls, nickel carbonyl and iron carbonyl. As sunlight breaks those apart, the nickel and iron atoms pop free and glow in the spectrum. Even more intriguing, that nickel to iron ratio seems to shift as the comet gets warmer, which hints that the chemistry running the show changes with temperature. The closer it gets to the sun, the more layers of material wake up and start evaporating. Each one tells a little piece of the story of where and how this comet formed. So where did it actually come from? At first, some researchers suggested it might have been born in the thick disk of the Milky Way, that older, puffier population of stars that hovers above and below the galaxy's main plane. But when astronomers rolled the clock back 10 million years, using precise star maps from Gaia, they couldn't find any nearby star that might have tossed it onto this path. The way it moves fits better with the thin disk, the same region where our sun and most familiar stars live. That doesn't give it a street address, but it does hint that it came from a fairly ordinary galactic neighborhood. Ordinary or not, it's ancient. A wanderer that's been adrift for untold ages before this one quick visit. Then came the part that confused a lot of people, the backward tail. Comet tails are supposed to point away from the sun because sunlight and the solar wind blow dust and gas outward. Threeey Atlas certainly has that classic anti-solar tail, the one stretching away from the sun.
We've got some fresh images of Threeey Atlas, a third ever interstellar object observed from Earth.
But Hubble and Gemini both caught something else, a bright wide plume facing the sun. At first glance it looked wrong, like the comet had flipped its physics, but it wasn't breaking any rules. It's a known illusion called an anti-tail. Here's how it works. Comets throw off both tiny powder and heavier grit. The small dust particles get blown away easily and form the normal tail. The heavier grains don't move as much. They hang behind, along the comet's orbit, like breadcrumbs scattered along a trail. When our viewing angle happens to line up perfectly with that orbital plane, that string of heavy dust looks like a spike pointing toward the sun, even though it's actually lying flat along the comet's path. So depending on when you look and from what angle, you might see a normal tail, a sunward spike, or both. Famous comets like Hale-Bopp and Suchenshan Atlas showed the same effect, and now Threeey Atlas has added an interstellar example to the list. And then there's another player always lurking in this game, space weather. The sun isn't calm. It constantly blows a stream of charged particles called the solar wind, and every now and then it throws a fit, a giant pulse called a coronal mass ejection, or CME. When one of those gusts slams into a comet, it can twist or even tear off its tail in what scientists call a disconnection event. We've watched this happen before. Back in 2007, NASA's Stereo spacecraft caught a CME snapping the plasma tail right off Comet Encke. In late 2021, Comet Leonard's tail kinked sharply and shed a piece as it crossed into a patch of turbulent solar wind. In 2023, Comet Nishimura lost its tail, regrew it, and lost it again while skimming the sun. And during the Rosetta mission, when the probe orbited Comet 67P, it even rode through a CME and measured the comet's plasma bubble getting squeezed while magnetic fields spiked and electrons surged. So when Threeey Atlas looks strange from one night to the next, the explanation is often simple. The sun's mood can rewrite a comet's shape in hours, but to truly understand how this visitor behaves, you have to see it from a better angle, like the one Mars just provided. Tracking Threeey Atlas, from Mars until it's gone. Every window to watch this interstellar visitor is short, and each one closes faster than the last. The first of those chances opened as Threeey Atlas made its October flyby near Mars's orbit. For a brief moment, the red planet became the best observation point in the entire solar system. Up there, several orbiters already circle Mars: NASA's MAVEN, the European Space Agency's Mars Express, and the ExoMars Trace Gas Orbiter. Each carries the kind of instruments a comet scientist dreams of using. MAVEN, short for Mars Atmosphere and Volatile Evolution, has a powerful ultraviolet spectrograph, basically a camera that doesn't take pictures but listens for the faint glow of atoms in invisible light. When sunlight hits water vapor escaping from a comet, it breaks those molecules apart into hydrogen and oxygen.
From images, we also saw that this object is active, which is an indication that this object is in fact a comet.
Each of those atoms glows in ultraviolet light at a specific wavelength, like a chemical fingerprint. MAVEN can catch that faint shimmer from millions of miles away. It's not theory, it's a trick the spacecraft already used once before. Back in 2014, MAVEN studied another comet called Siding Spring when it brushed past Mars and wrapped the planet in a giant hydrogen cloud. Now, scientists are running that same play again, hoping to catch the ghostly halo of hydrogen and oxygen building around Threeey Atlas as its ices boil off in sunlight. ESA's Mars Express joins the hunt from another angle. It carries instruments called SpyCam and Omega, which specialize in identifying molecules through their fingerprints in both ultraviolet and infrared light. The ExoMars Trace Gas Orbiter adds two more instruments, NOMAD and ACS. These are extremely sensitive spectrometers designed to sniff out the faintest traces of gas in the Martian atmosphere. But right now, they're turned toward the comet instead. If Threeey Atlas is venting water, carbon dioxide, carbon monoxide, or even cyanide compounds, these spectrometers can spot the signs, thin colored lines hidden in the sunlight reflected from its coma. Together, these orbiters act like a remote laboratory floating around Mars. They can measure not only what's leaking from the comet, but how quickly it changes from night to night. Their imaging cameras follow the cloud of dust and gas, watching to see whether it expands smoothly or erupts in sudden jets. Even simple brightness readings help reveal if the comet's activity is steady or pulsing. It's like tracking the breathing pattern of an object millions of miles away. The timing could hardly be better or worse, depending on where you are. While Mars has a perfect line of sight, Earth does not. From our position, Threeey Atlas is sliding almost directly behind the sun, making it practically invisible to our telescopes. When a comet passes that close to the sun in the sky, the glare overwhelms every instrument we have, no matter how powerful. Even the best observatories must pause their tracking until it swings back out again. But the spacecraft orbiting Mars don't share that problem. They sit at a different angle, far enough from the sun's blinding light to protect their instruments, but close enough to catch valuable data. That's why early October became such a crucial window, one of the few moments when high-quality ultraviolet and infrared readings could be made while Earth-based telescopes were essentially blind. Next comes the real test, the comet's closest approach to the sun, known as perihelion, at the end of October. This is the peak moment of drama, when sunlight hits hardest and the comet's ices boil fastest, turning the coma into a huge glowing shroud. But there's a problem. When that happens, Earth is still in a terrible position. The comet will lie only about 13 degrees away from the sun in our sky, far too close for most telescopes to aim safely. Even the Hubble and James Webb Space Telescopes have strict do-not-point zones that forbid them from staring near the sun's glare.
The plume of gas around it is mostly carbon dioxide, 95% by mass, based on the Webb telescope data.
Their giant mirrors could literally burn if exposed to that much heat. So while the comet reaches its most spectacular phase, nearly every major telescope on or around Earth must sit quietly, waiting. That's when a different kind of spacecraft steps into the spotlight. One's built to stare directly at the sun. The Solar and Heliospheric Observatory, better known as SOHO, has spent decades watching the sun's outer atmosphere by blocking its blinding disk with a small metal mask. Every so often, a comet drifts through that field of view, its tail blooming in real time as it rushes past. ESA's Solar Orbiter and NASA's Parker Solar Probe carry similar wide-angle cameras that could also catch Threeey Atlas as it passes through the glare. ESA's early predictions are cautious. SOHO's cameras cover a large area, but the comet may simply be too faint to stand out against the sun's brightness. Still, even one lucky frame, one moment where its tail curves or brightens, would be priceless. It would capture the exact instant the comet was shedding dust and gas at maximum speed, when sunlight was pounding its surface and every other telescope on Earth was forced to look away. For comet scientists, that single snapshot would be worth gold. Once Threeey Atlas rounds the sun and begins heading outward again, the geometry changes. The glare fades, and new spacecraft get their turn. This time, the European Space Agency's Jupiter Icy Moons Explorer, nicknamed JUICE, takes the lead. Between early and late November, roughly from the 2nd through the 25th, JUICE will train its cameras and spectrometers on the fading comet. By then, Threeey Atlas will still be active, but no longer lost in sunlight.
Good amount of data, more than 100 observations. We know its trajectory fairly well.
Its tail will probably stretch millions of miles behind it, the dust cloud still dense enough to reflect sunlight, and the gases still glowing faintly in infrared and ultraviolet light. Over those weeks, JUICE can record how quickly that activity fades, how the gas thins, how the dust grains change size, and how the coma's shape shifts as the nucleus slowly cools down. It's a rare chance to film an interstellar visitor catching its breath after a near pass with our sun. Later on, as the comet's tail stretches farther into space, other spacecraft might cross faint wisps of its debris. Missions like Europa Clipper, Hera, or Lucy, if any of them detect a small jump in dust or charged particles at just the right time, that would count as a direct sample of the comet's trail. Even a few particles would be a scientific jackpot, a literal taste of material from another star system. These observations aren't just chemical trivia, they're clues about where this traveler was born. The gases it releases, the metals hidden inside its dust, even the ratios of carbon and oxygen, all of it tells a story about the environment it came from before it ever reached our sun. But light itself tells another kind of story. As the comet spins, its bright spots, patches where gas and dust escape faster, move in and out of view. That makes the overall brightness rise and fall in a steady rhythm, like a rotating lighthouse. By tracking those ups and downs over many nights, scientists can figure out the comet's rotation period. If that rhythm repeats smoothly, it's a sign of a natural, unevenly shaped nucleus. If it were perfectly mechanical, blinking like clockwork from every angle, that would raise questions. But so far, Threeey Atlas behaves exactly as any comet should. Its brightness changes are soft and uneven, ruled by sunlight and spin, not by anything unnatural. By December, as the comet makes its closest pass to Earth, roughly 170 million miles away, it will already be too faint for casual stargazers, but still within reach of the world's largest observatories. JUICE will likely wrap up its campaign around then, handing the baton back to ground-based telescopes as Threeey Atlas drifts toward the region of Jupiter's orbit and beyond. The mountain of data collected during these few short months will be studied for decades, not only to understand this particular comet, but to sharpen how we recognize the next one. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.